As introduced, I'm Isabel Gerritsma, working as a researcher at Deltares. And in this presentation, I'll share on computer vision applications in the field of water quality management, starting with a bit of the recent development in computer vision, whereafter I'll go into a project at Deltares where we actually tested various strategies of some of these computer vision methods. A big leap, of course, was the change from classical methods that were often feature-based and needed to be manually tuned and needed handcrafted features, from going to, on the right side, deep learning architectures, where actually these features are learned by the model itself from the data automatically. And this already opened the floor to way more scalable models and way more adaptable models. Sorry? Okay, thanks. I hope you can hear me now. We'll continue with more rapid advances in the past few years, actually, in computer vision. Which contributed all to more generalization in the models across different tasks and domains. On the left, we see transfer learning, which actually allows a pre-trained model to, with new data, use the old knowledge from the pre-trained model to actually transfer to a new specific domain. Then foundational vision models are general purpose models that are trained on a huge amount of vast and diverse, in this case, visual data. And they serve actually a purpose to be general across more domains and tasks. And then lastly, grounding and multimodality actually include different types of data. So for example, like text, image, video, and audio into unified models, also contributing to this generalization. Then very few, because there are a lot actually in the field of water quality, but a few examples of how these recent developments, but especially deep learning, contributes to the water quality research field. And on the left, you see the automation of CCTV inspection. So here actually a deep learning model detects and tracks fat on water in an underground sewage system. In the center, you see the detection and tracking of floating vegetation in lakes. And except only optical data, we can also use various other input data types like radar, sonar, or thermal plumes that you can translate to a visual image, and where computer vision actually can handle. Going from these trends and developments, I'll show you one project at Deltares where we actually tested computer vision in various strategies. So also showing you a bit of the trade-offs between how you can use these models. The project itself was a laboratory flume experiment where we wanted to know the vertical distribution of macroplastic elements in rivers. You'll see on the right the flume setup with the cameras set up beside it. And we tested several types of plastics, like here you see like the plastic bags or blue cups. And the objective was to track these plastics across the frames. So we collected hours of video data with all these types of plastics, and this needed to be analyzed. Manually analyzing all this video data would have been like an enormous task. Opening the floor to trying some computer vision methods. We tried in this project 3 strategies. The first strategy will highlight the classical method strategy, and then the second and the third strategy were the use of SAM2 by Meta. For the classical computer vision method, we used filter-based methods that detected features in the frame by frame. And filters were like color filtering. For example, here, blue worked pretty well for the blue cup, but also filtering on geometry. This worked very well for specific, more simple plastic types. But when a plastic became more translucent or had more arbitrary shapes, or it would change during the experiment, the classical computer vision method would not suffice. So although it was super fast, sort of easy to deploy, although you had to manually tune it for every type of plastic, it did not work for, it was not scalable to this project, but also probably not to other experiments. Then for the second and third strategy, as I mentioned, we wanted to try SAM2, which is a reasonably new zero-shot foundational vision model. And as I explained, a foundation vision model is like a huge model trained on a huge data set, which makes it quite general. It has a purpose to be general. And then the zero-shot learning enables it to predict on tasks or classes that it has not seen in the training, which would be like, it's actually quite an extra step to this generalization in models. The first try was actually just directly using SAM2 as is, which did not generalize well across all the types of plastics again. But when we fed it a few examples created by manually prompting, and then feeding these masks of these prompted plastics into the model, actually SAM2 sort of became a few-shot prompting model, which worked very well. It could generalize all types of plastic that it would see in the experiment. And so it was very accurate. And a third strategy that actually also worked really well, but it was a bit of a different function, is that we use SAM2 as a labeling tool. So in order to fine-tune a CNN later on, which is way more lightweight than SAM2, because SAM2, like this foundational vision model, is quite extensive. And this lightweight CNN would allow us to, for a follow-up project, transfer this CNN to an edge device, as we actually saw in the presentation by the tiny machine learning. Although then an edge device that's a bit bigger than the microcontroller. And actually using SAM2 directly without having these few-shot examples, we could actually create a labeled data set from masks and image pairs very well to fine-tune the CNN, which then trained on these specific plastics, of course, worked really well as well. Comparing these three methods actually shows that for the classical methods are super fast and kind of easy to deploy, although you have to manually tune them. They have the con that it's often not generable enough for these type of experiments that have very complex and diverse conditions. But using SAM2 for either labeling as a labeling tool or tweaking it a bit so it can do few-shot prompting, it worked very well. So to conclude, we emphasized the model generalization by foundational visual models, transfer learning, and multimodality, actually key for the scalability and adaptability of AI systems. And then looking ahead, these models can actually be tested very well in field and lab deployments, where in the computer vision field, computer vision has actually quite a high TRL, technology readiness level, but the constraints coming from these specific settings, like we saw in the Flume experiment, still require these trade-offs in scalability, practicality, and robustness. Thank you for your attention, and I'll be open for questions.